Hello class, Professor Anderson here. Let's talk a little bit about work. Work is something that we've heard a lot about, right? We know that word, work. But let's talk about what it means in a physical sense, right? In the physical sciences, what do we mean by work? And what we mean is the following. Work is going to be defined as this, okay? This is a good place to start. We're going to get a little more complicated in a minute, but let's start with this idea that work is just going to be defined as that. And there are a few caveats here. Constant force that we're going to apply, constant theta, angle between the two. All right, we'll get to the more complicated version of this a little bit later on. What we're going to see is work is actually an integral. But for now, let's start with this definition. Okay, what does this mean? It means the following. Let's say I take a box and I'm going to pull on that box with a force F, and the box is going to slide across the ground a distance d. D is a displacement, and so we put a vector sign on it, and the angle between those two is what we call theta. How much work do you do on the box? You do FD cosine theta. All right? So let's see if we can understand how this applies to real-world problems. Let's say that you move a box horizontally, and we're going to work against the influence of gravity. What does our picture look like? Here's our box. We have to hold it up against gravity, and we're going to move this thing horizontally a distance d. Okay, those are both vectors. Let's calculate the work that is required to do that. The work that we have to do, our lift force over that distance, is going to be this, F d cosine theta. F is just the lifting force. D is the distance that we go. Those are scalar quantities. And then we have the cosine of the angle between them. What is the angle between those two? It's that right there, and that has to be 90 degrees. So, what is the work? It is F lift times D. What's the cosine of 90 degrees? 0. How do you remember that? Well, you go back to your circle. And as I go around the circle, I can draw a triangle. This side is cosine, this side is sine. And so as I go up to 90 degrees, the cosine shrinks to 0, right? The sine goes up to 1. So this, in fact, becomes 0. And so it requires no work to lift this thing horizontally, to move it horizontally if you're holding it up. Now, we know that something seems a little strange, because if I'm holding up this object and I move this horizontally, it feels like I'm doing work, right? If this is a weight, something bigger than a pen, right, and I move it along horizontally, I'm getting tired doing that. Why do I get tired doing that? What do you guys think? I'm asking you.
You're lifting it.
Okay, what was your name? Carlos? Can you hand Carlos the mic?
Because you're lifting the pen.
Okay, Carlos says because I'm lifting the pen. Let's pretend we've already lifted up here, and now I'm not going to lift it up or down anymore, but I'm just going to move it horizontally, right? We just said I don't do any work on it, but what we're talking about here is physical work, but that's not what I record in my body. What do I record?
I don't know.
Okay. Some other kind of work, right? What do you think, Brent?
The muscles moving to hold it in 3D space.
Yeah, exactly. And what do we call that? We call that physiological work. Okay, what we're talking about here is physical work. What is work in physics? But what I observe as a human on this planet is I have to do physiological work. And that means that there's blood flowing through my body that suffers from friction, which generates heat, which radiates as electromagnetic waves. Muscles twitch, contract, and expand. All of that requires me to burn energy, right, and create physiological work. Aiden, did you have a question?
Yes. Wouldn't the work be zero because your horizontal distance is zero?
Okay.
Upwards force has no horizontal component, no x component to it.
Okay, the horizontal distance is not zero, right? It is distance d. All right, so I have moved this thing a distance d, and we're assuming that I'm moving it slowly. I'm not accelerating it or anything like that, right? So it definitely moves a distance d. That is non-zero. But the other thing you said is exactly correct. Because there's no component of the force along that direction, I don't do any work on it. And that's sort of what's buried in here. This cosine is really picking out what component of the work is in the direction of movement. In this case, it's zero. Good. Okay, let's try the different problem where we lift it straight up. Okay, guys, let's look at a slightly different variation of this work problem. Instead of moving the box horizontally or some angle, let's move it vertically. Okay, so here's our ground. We're going to take this box and we're going to lift it with a force, F lift, and we're going to lift it vertically, a height h. Okay, so this is really a displacement. That's really a displacement. Displacement, of course, has a direction associated with it. If I'm lifting this box vertically and I am moving it vertically, everything is vertical. What is theta in this case? Theta is the angle between the force and the displacement. And if those two things are parallel, then theta is zero. Okay, they're in the same direction. And so now we can calculate the work based on what we said over there. It's FD cosine theta. So the work that we do in lifting this is F lift times h times cosine of 0 degrees. So how do we remember what cosine of 0 degrees is? We go back to our unit circle. Here's our triangle. This side is cosine, this is sine. And so as I rotate this thing down to the horizontal axis, the bottom side of this triangle gets bigger, the sine goes to 0. So cosine of 0 is actually 1. Sine of 0 is, of course, 0. And so we get F lift times h times cosine of 0, which is 1. Now, if I lift this thing slowly, then what is F lift equal to? Slowly just means I'm not going to accelerate it very much. We don't have to worry about, is this thing acquiring a lot of kinetic energy? Okay? And so if we lift it slowly, then the force that I have to apply to lift this box is just mg, the weight. And so we get the work that you do in lifting it is just equal to mgh. Now, if I lift it very quickly, it's a different problem because F lift is now bigger than mg, right? If I want to accelerate that box upwards with some non-negligible acceleration, then it's going to be bigger than mg. And that just means that the box is going to have kinetic energy then. Okay? If we lift it slowly, we're only worried about increasing the potential energy of the system. And this looks really, really familiar, right? MGH. Wait a minute, isn't that our good old gravitational potential energy due to gravity? It looks like whatever energy I put into the box in lifting it is now available to be released in kinetic energy if I drop it. All right? And so we say we've done positive work in lifting this box. We've lifted it up. We've put in MGH.